lecturers, speakers, and students, very much the students. So we are now on Friday, last day of the school. I was personally very impressed by everyone, the student, the quality of the questions, the quality of the lectures. So we will have another very exciting day, starting with Professor Mauro Olivieri from Roma La Sapienza, who is going to give a pretty interesting talk. And then during the day, we will also have other talks from one of our industrial sponsors, Fabio Previtali from Alba Viva, who is certainly going to tell us quite a lot interesting thing. And then to close the school, we'll have Professor Matteo Valero, who is the director and the founder of the Barcelona Supercomputer Center, which is very much behind the entire school, and is going to give us a kind of visionary talk at 3. And then we will conclude the day with the Chief Executive Officer of ACM, Vicky Anson, who is the primary sponsor and the reason why, the primary reason why we're having this school. This is the ACM school. It will tell us, some more information about ACM for all of you who are not very familiar, and also will confirm that all students who have attended, most of the classes, we receive a special token from ACM, a 1-year free subscription to ACM as a student. And then she will also confirm the other token, a monetary token that will be given, will be granted to the top 3 poster according to the vote we did yesterday. And then we will also have some time during the day, the head of the HR department at the Barcelona Supercomputer Center, because we are in a hiring movement. There is a lot of hiring opportunity, especially on the domain covered by the school. So Mark Gonzalez will tell us something about the opportunity at the Barcelona Supercomputer Center. So let me now start saying a couple of words about Mauro, who is not only an excellent scientist, but is also a very nice, good friend of us and good friend of the Barcelona Supercomputer Center, and he's been involved in all our projects. As I said, Mauro is a professor, a full professor at the university.
Fabrizio, we are losing your voice.
Can you hear me now?
Yes.
Okay. Yeah, I'm now in a different place. I'm now in Barcelona from home, so I don't know. Anyway, just a couple of words of his background. He got his master's degree and the doctoral degree from University of Genoa, which is his hometown, and then of course he went through a number of steps in his brilliant career. And his main research interest, as you will see from the lecture, are on microprocessor, chip design, and so forth. And as I said, he's now full professor at the University of Roma La Sapienza, and very active member on a number of projects around the development of European processor technology. So without any further ado, of course, you can get more information from the bio posted on the web. Without any further ado, let's leave the floor to Mauro, and wish Mauro best of luck with his lecture. So Mauro, the floor is yours.
Thank you very much, Fabrizio. I will try to share the screen. 1 second. Can you see my slide?
Yes.
Okay, thank you very much. Okay, so first of all, thank you, Fabrizio, for the kind introduction. I have to say I'm not a full professor yet. I am an associate professor. Thank you very much anyway. Okay, one thing, as the other lecturers probably already told you, I cannot see the chat while I am presenting the slides. So there is a PhD student of mine that is participating in this lecture, and he will assist me possibly in checking if there is any comment or question on the chat during the lecture, or any problem, whatever. By the way, I will, of course, let you ask questions, and whenever you want, of course, I will anyway open some question and answer sessions so that you can open your microphone and talk freely. I plan to have a 10 minutes break or more or less every hour. Okay, so I think we can take some rest during the discussion. I hope you are not, sorry, 1 second, because I cannot go on. Okay. I hope you are not too much tired after so many days and many hours of lectures. I hope that you will enjoy this one too. You can see here some links to my profiles. I also have very recently, a few days ago, opened an Instagram profile, but that is only personal entertainment, and I don't suggest to follow that unless you are interested in learning some Italian language. Okay. As the other lecturers did, I would like to understand something about you. First of all, okay, I already know that most of you are PhD students and postdocs. I would like to know if some of you are professionals, I mean, in the academic environment or in industry. You may write on the chat if you are working as a professional in computer engineering or computer science. Okay, if you write on the chat, I ask Marcello to count how many of you are already in an advanced stage of their career. So I'm waiting a few seconds for you to write. Thank you. And okay, regarding your background, I already know that most of you have computer science and computer engineering background. So I'm not going to ask you if you have this kind of background, but I would like to know if there is any of you that has an electrical or electronics engineering background. If possible, please write on the chat that one, because, you know, I would say that my lecture is going to be a bit, let me say, particular, probably well connected with the very first lecture of this school, the Monday morning lecture by Professor Uri Weiser, because it is going to talk about the connections between the electrical circuit level and the architecture, computer architecture level. So, Marcello, any electronic engineers around? Can you hear me?
Hello, Mauro. Hello,
Yes.
everyone. Yes, there are 4 professionals from now, and many other electronics engineer, maybe 5, 6, 7.
Okay, okay. That's great. That's great. Thank you very much. I am asking this because this is actually my background, as you can probably imagine. And that's also the reason why I wrote in the chat, good morning, HPC experts. In fact, I am quite sure that you know much more than me at the software level and the system level in HPC HPC systems. Okay, And that is not bad. You know, there is a famous quote that I like a lot from it is by Richard Feynman, Nobel Prize in physics, and the quote says, "If you are the smartest person in the room, then you are in the wrong room." So that's why I'm very glad to be here talking with you. Who are probably more expert than me in the software layers of HPC systems. Okay, so we can probably discuss something very interesting. For those of you who are particularly interested in this, let's say, particular point of view, that is the connection with the hardware and circuit level, I would like you I will propose you some exercises, some little questions. You will see at the beginning, it will be very easy and probably even trivial for you. But if you are interested, I would like you to ask, I would like you to form a little team of 2 people if you want. You can use the private chat for taking an agreement on that, and send an email now to this address here that I created, dedicated to this purpose, so that during the lecture, or even a little after the lecture, you can send your answers to the proposed questions from my side. And the only purpose of that is to have some feedback from you, and also some feedback from my side to you. And I will also tell you if someone is interested in this field, and I'm talking in particular to PhD students, and may be interested in a subsequent career in this particular field of study. I will consider the answers that maybe you sent me for recruiting some postdoc, for example. Okay, we are always looking for smart people for participating in our research team. Why would you be interested in joining the research I am doing? Maybe if not for the topic, for the place. Sapienza University of Rome is the largest university in Europe, and the department I am involved in is the so-called DIET, that is Department of Information Engineering, Electronics and Telecommunications. This is the main entrance, as you can see here, and we are 300 meters airline from the Colosseum. This is not kidding, it is true. Okay, so the venue is very nice if you are interested to come and visit us. Okay, I have to say some of the things that I'm going to talk to you are the results of the work of a team. The team is the Digital System Laboratory at Sapienza University. So you can see here the people that actually contributed to this work. And so here we are. Oh, sorry. So this is well, I would say very detailed summary of the lecture that I will give this morning. Okay, the first part is done. Okay. I would like, first of all, to introduce some, let's say, context. I think this is very important. I would say in the whole lecture, I will probably not teach you many new things that you never heard of. But what I would like to do, the goal of the lecture, is to offer you some new viewpoint, new point of view, a new way of connecting concepts, that you may not have thought about. If at least 3 or 4 of you will get this outcome from this lecture, it means that this lecture is a success. Okay, so I will first go through the perspective of supercomputing and embedded computing. In this, I will make some connections to previous lectures, especially, as I told you, from Professor Olivieri and Professor Luca Benini, a good friend of mine. And also we'll give you some background concept regarding the silicon, let's say, level that is important to keep in mind. And then I will revise something that you may, for sure, you know, I mean, but again, I will offer you some new perspective to look at, hopefully, regarding the fundamental laws of performance evaluations. Okay, performance evaluation in high performance computing. When I say high performance computing, I'm referring to both what we call supercomputers in the traditional terms, traditional meaning of the term, and high performance embedded computing, that is high performance computing on the edge. That is a concept that I will focus a lot on. We will go through 2 case studies. In particular, the first one is some project that you already heard of for sure from John Davis' presentation and from Professor Jesus Labarta. I will be glad to give you some insight view at the microarchitecture level regarding this project. And finally, we will finish with an educational case study where we will try to apply all the things that we have discussed during the morning. Okay. By the way, is there any important question regarding the organization of the lecture? Okay, Marcello, feel free to interrupt me if there is any relevant comment coming out of the chat.
Yes, absolutely.
Thank you. So let's start with some history here. If you consider computer system evolution since the very beginning, sorry, opposite way. I'm talking about the 60s and maybe the 50s even. You may say that at that time, every computer system was HPC, high performance computing, because the only market for computer system was the solution of complex calculation in the scientific world or financial applications. And there are some famous quotes which are not very sure that they are true, but you know, president of IBM is said to have said there is a market for maybe 5 computers in the world. Okay, it is not sure if he never said something like that, but anyway, this gives you the idea that at the beginning everything was only intended for high performance computing. Okay. Later on, we learned very soon that there was a diversification of applications and also of types of systems, at least 3 big categories. You know, this is the scenario that we may we may have found 25 years ago. High performance computing on one side here, the so-called personal computers and the servers, which are less high performance, and the new field of embedded computing, small devices which actually incorporate computing systems. But nowadays, we know that the scenario is even different, even more diversified. You know, on the very right side of the picture, you have high performance computing in the traditional sense of the term and the new data centers, which are managing the famous big data, you know. We still have a large market for personal computers. Tablets and smartphones represent a fundamental evolution of the market of computing, but also the automotive market is a huge market, is a huge let's say context of application of computer systems. I always tell my student that in an average car there are more than 100 microprocessors, and the research in computing for the automotive market is much more, the investment is much larger than in engine technology. And finally, we have the huge market of IoT, the Internet of Things, small devices which are more and more capable of computing locally. This is what we call the edge of the IoT, so that you have, again, computing applied in this particular device. Correspondingly, if you look inside, what you find is a different kind of microprocessors. Going from the very high performance microprocessors here, of course, maybe the models that I am showing here are not the very latest one, but this doesn't matter. Okay, you know, this is just to convey the idea. Here you have ARM that is actually dominating the embedded system market. And the Cortex is again ARM, despite the fact that this is fabricated by STM, and even smaller devices, especially in the IoT systems. Okay. So we are, at the moment, we see this big diversifications of microprocessor technology and microarchitecture. Okay, this is, let's say, the present scenario, but we would like to understand from the history what is going on for the future. I know that you already saw this chart, so I will go through relatively quickly with this. This is a famous chart that everyone is using, okay, showing the evolution of several aspects of microprocessor technology over the last decades. So the number of transistors per die, per chip, has increased exponentially and is now saturating. It is probably not yet saturating so evidently like other parameters are doing, but for sure we are a bit more at the limit, especially the limit from let's say cost convenience. Okay. Regarding the performance, this you have saturation here, performance of single thread applications. The frequency, it is very clear since, it has been very clear since 2005 that the frequency hit a plateau. We are not going higher than a few gigahertz, even in the highest performance systems. The power consumption has increased exponentially, but at the moment we are in the range of hundreds of watts in the higher, of course, a very high performance, and we cannot go higher than that. Not related to the let's say the absolute power consumption, but the big problem is power density. You know, the watts divided by the area. Okay, what we call power density, because this is related to the increase in temperature of the chip, and it is causing a lot of problems, including costs, because you need cooling systems which have a high cost. and the number of logical cores. What are the logical cores is threads, you know. So since you cannot increase the performance anymore, instruction level parallelism is not going to give you so much improvement in your performance. And it is clear that many applications can be programmed as a parallel execution. Multi-threading has started since again the beginning of the 2000 era. Multi-threading can be implemented as multi-core, where you map your threads in different cores, or as Uri Weiser presented, you may have multi-threading in a single core, simultaneous multi-threading. Okay, we will get back to this later in the lecture. Okay, so overall, the saturations that you see here and that you see especially in the frequency and in the number of transistors that you integrate in a die is all mainly related to the problem of power density. Okay, you cannot afford to have an increasing power in a single chip. So what happened in this respect in high performance computing? 1 second, I would like to see. Because I see a black stripe on the top of the screen. Marcello, can you see the title of the slide?
Yes.
Okay, okay.
For us,
so,
it's clear.
Okay, okay, sorry. So there is no problem for you. That's great. So what happened in the regarding the power consumption in high performance computing? This I am talking about the famous top 500. I mean the fastest machines in the world. If you look at the data on the internet, you can see that the power efficiency is usually measured in operations per watt. In the high performance computing environment, operations is very often considered the gigaflops. Okay, but it may be whatever. For example, in a graphic application, computer graphics application, maybe number of pixels processed per second. Okay. For the case of gigaflops, you have this gigaflops per watt, and you see that this that we call power efficiency has increased exponentially. This is a logarithmic chart, has increased exponentially during the history. This is, let's say, very good point. It means that both the microarchitecture and the technology allowed to make this point. Can you mute your microphone, please? Thank you. So to give some numbers, what we expect is that in the famous exascale era, we can get this power efficiency between 33 and 50 gigaflops per watt. This comes from some calculations that we made at the BSc, and it is also mentioned in a publication regarding the perspective for exascale in Europe. And of course, the target technology should be very advanced. By the way, one point this I would like to mention for 1 second. When you look at this technologies, very advanced silicon technologies in the field of edge performance computing, you are not targeting those because they allow, for example, higher clock frequency, much higher speed. You are targeting those because they are smaller the feature size is smaller, and therefore you can guarantee the density, and in the end you are able to build a machine that can be hosted in a relatively small amount of space. For the performance that we are targeting in the exascale era, we need these technologies just for this, and also for reducing the power, because the smaller the size and the smaller parasitics, and therefore the power consumption is smaller. So what happened in the history of supercomputer? If we look at the very beginning again, you remember very early computers, memory capacity was the problem. What is interesting, that all the fundamental computer architecture concepts were already invented at the beginning of the 70s. Cache memories, virtual memory, memory management, operating system concepts were all already there. Okay, that's interesting. Then we faced the first rise of what we call hardware acceleration. We will get back to this in detail. In particular, vector computers are computers that include some special hardware microarchitecture for supporting vector calculation at high speed. The need for vector computers came out when the memory capacity was solved, let's say, thanks to the new silicon technology. But the processing speed on scientific calculations was the main limit. And therefore, since the scientific calculation is characterized by matrix calculations, matrix algebra, even more today with the artificial intelligence applications, vector computers seemed to be the answer. Okay. However, it may be surprising, this period has a beginning and an end. Actually, it came out, two things came out in the 90s. The first is that it was not so difficult to achieve a very high processing speed, but what you face now was the memory bandwidth. Many problems are memory limited. And this is one problem, that is, it was the memory wall. So it was not so much convenient to make more and more, faster and faster vector calculations if you cannot access the memory so fast. And the second thing that happened is this, that is, let's say, the advent of personal computers. Personal computers pushed for the development of technologies that allowed to have a huge amount of relatively high performance microprocessors available. And so in the end, it came out that building parallel architectures with commodity CPUs, the same CPUs more or less that you have in personal computers, was more convenient economically, financially, than building very high cost vector processors that you cannot sell to a very large market. This is what Matteo Valero calls the killer CPUs. Okay, for a very long period of time, vector computers were practically killed. There was only maybe one company that still fabricated the vector computers. And then we come to the present era that started more or less after 2008. As I already mentioned, we faced the problem of power consumption. We hit the power wall. Okay, so the problem is not only to have fast memory access and memory bandwidth, but to limit the power consumption, in particular to limit the power density and to increase the power efficiency. And there is only, I would not say not only one way, but let's say a very, let's say, general way for achieving higher power efficiency, that is hardware specialization. In this case, in this sense, we may talk about the renaissance of hardware acceleration units, including vector processors. In particular, at the beginning, we started using GPUs, and we are still using a lot of GPUs in supercomputers for vector acceleration. Sorry, not for vector, only for vector acceleration, but for hardware acceleration in general. But there is one reason, again, because GPUs came from a high volume market that was the graphic boards in personal computers. That's why they were the first device that was available for accelerating computation with a relatively limited power budget to increase the power efficiency. Some of you may say, okay, but the GPUs are famous for consuming a lot of power. Yes, that's true. But if you consider the ratio between the power and the computing speed, no doubt that that GPUs achieve a higher performance, higher efficiency than a general purpose microprocessor. So I was telling, the first example is GPUs for trying to improve power efficiency with a specialized hardware. And I will also say specialized software for programming GPUs. But there is a lot of interest and investments nowadays, again, in vector computing, as you probably heard, and as I am going to talk again in this lecture. Okay, so what we are seeing in this moment is a renaissance of hardware accelerations, including and especially including vector acceleration. Even companies that are traditionally not interested in this kind of microarchitectures, they are now expressing interest in this. One example is ST Microelectronics. You may not expect that a company that is specialized in embedded system market, they are actually interested in developing vector acceleration inside their system on chips. And this is what they are doing because I am in contact with them regarding this. Any question, by the way? You may turn on your microphone. Great. Okay, so that was the evolution of high performance computers, okay, in the traditional sense of the word. Let's look at the other side of the picture. You remember on the right side, you have very high performance computing systems. On the left side of the picture, the smallest devices on the edge, okay. Embedded system for IoT edge. Okay, edge computing. This slide is a courtesy of Luca Benini. Okay, the very, let's say, general scheme for an edge computing device is that you have some sensors taking information from the environment, and you have some local processing. Usually in the traditional way, it is a microcontroller, like, for example, a Cortex from ARM, with very low power budget, but also very low performance, relatively low performance. And then you have transmission of data, usually wireless, with some particular protocols. For example, I don't want to go through this, but for example, LoRa is characterized by covering a very long range, but very, very slow bit rate. And this is again for saving energy. But nowadays, what we have is that the requirements for edge computing has changed a lot. So you can get a much higher, so you must get a much higher computing speed at more or less the same limited power budget. This is a revolution that is happening. It started very few years ago. Let's say 5 years ago, something like that. Sorry. Okay, there is something that is missing in this slide, but okay, I will tell you. So in the end, what you have here, let me make it clearer. Okay, in the end, in the edge computing device, you end up to have, again, accelerators, hardware accelerators, to guarantee very high power efficiency, intended as the ratio between achieved computing speed and power consumption. And the target computing speed is closer and closer to the computing speed that you have in a microprocessor that is used in high performance computing. So in the end, what you have is a kind of a touch between the extreme part of your picture, the same microarchitecture concepts, for sure. And in the future, even the same devices, in some cases, will be used in edge computing as well as in very high performance computing system. This is something that never happened. So we are, let's say, entering a phase in which let's say the boundaries between different application domains and consequently between different engineering specialties are broken. Okay, so I was telling you 1 second ago that ST Microelectronics is hiring engineers with the expertise in vector computing. That is absolutely something with no previous example in the field. Okay, by the way, any questions related to this historic evolution that I would like you to understand very well? Please turn on the mic if you want. Okay. Okay, so after going on with the lecture, I would like to give you some background concepts for those of you that don't know this aspect at all regarding the design flow of microprocessors in general, of any integrated circuit. Most of you will not be involved in this at all in their career, but it is more and more evident than the connection between the technology that is behind your computer system is something that you cannot ignore anymore. There is an important example regarding this. Consider the BSC, Barcelona Supercomputing Center, which has a very prestigious history of computer science and computer engineering research and absolutely outstanding achievements. Well, in the last 3 years, it started investing and hiring people for the development of silicon chips. Okay, so you see that there is this connection that is stronger and stronger between the computer science intended as software layers of the supercomputing world and the hardware, even the silicon that is involved in fabricating computer systems. So I will not go through in detail, of course. However, what you have you start from the system architecture specification, you go for RTL design. Here it's there where you used your system Verilog or VHDL descriptions. You do the synthesis, you do technology mapping. That means you map the synthesized microarchitecture on a cell library. Here is where the technology enters the scene. Okay. Then you have the so-called physical design. This is a famous separation between the front-end design and back-end design. Physical design is itself very, very complex. It includes several steps regarding let's say the several steps to arrive at the final layout. What is more difficult in this is to arrive at the timing closure, so to verify that everything is properly working and it meets the timing requirements. In the end, you get to the fabrication. It means that you send your files, which are in a particular formats, to the foundry. The foundry sends you back samples of your chip, usually 3 months later. And the chip must be must be soldered on a board that is usually fabricated for that purpose to implement the so-called ring up. That is, try to see if your chip is alive. Okay. This lecture is not going to show this, of course, this design steps, because it is not the topic that you are interested in. But what is important is to understand that the types of values that you are looking at the different steps of the design, at the beginning, they are logic values, or in some cases, even symbolic, and of course, numbers. Then you start having delays after you synthesize. And this is a big, let's say, the first big step, okay? You deal with delays. You don't deal with delay when you write a program, okay? Explicitly. When you do synthesis, hardware synthesis, you do. And another big step is when you get to physical design. Here you have voltages and currents, and also geometry. That is the area that is occupied, that is used by your device. Okay, here is where power consumption is coming into play. Okay, what I will show you is that we must find a way to keep these different levels of abstraction connected somehow. Of course, when you design your system architecture, or when you are programming your microprocessor, you don't know the details of your chip. But I will try to convince you that it is necessary that you know the laws that are behind the performance of the underlying hardware structure. When I say performance, I mean not only speed, but power consumption in particular. Is there any question?
Mauro, there is a question maybe related to some previous slides.
Yeah.
And
I can stop sharing 1 second, and I will try to.
Yes, if you want, I can read the question. Christian Ramirez asks if the hardware is adapted to the workloads when we call about edge computing or supercomputing or automotive embedded system and others.
Christian Ramirez, can you turn on your microphone and ask the question, elaborate a bit, because I'm not sure of what you are referring to. Hello? Okay, no problem. In case you can turn on your mic, please ask the question so that I can try to discuss that with you. I see that there is a comment regarding yes, the email address. I forgot.
Yes.
Okay. My fault. I'm sorry. I will go back 1 second. There is an error in the slide. Sorry, I will stop sharing for 1 second. And I will correct so that I can show you. Okay, done. So I'm sharing again. Going back. Okay, can you see the slide?
Yes.
Okay, there is a dot here instead of an underscore. I'm sorry, there was a mistake in the slide. So it is summerschool.olivieri@gmail.com. Marcello, you may try to write an email and see if it works.
Absolutely.
Okay, so let's go back to our discussion. Any question related to the concepts that we have introduced?
May I ask you just to clarify?
Yes.
What you're telling us is that software developers should understand the underlying architecture of the microprocessor, or that specific, I don't know, perhaps who is developing a framework like TensorFlow or things like that should know how the underlying architecture is laid out?
Of course, not in detail, but the mechanisms that govern the performance and especially the power efficiency, so the ratio between the performance and power consumption. Yes, it is my. I am convinced of that, and I will try to convince you with some examples.
Okay, thank you.
Okay, before going to a first short break, okay, let's build a supercomputer. Of course, this is a kind of a joke here, but not too much, because in the end, the very basic steps are here, conceptual steps, of course. Okay, you start with the very basic component. You may say it is a microprocessor core. We all know more or less nowadays that modern microprocessors are multi-core, but in a single core you may have single thread execution, or maybe if it is supporting multi-thread in the core, maybe even multiple threads. Okay, usually the chip that implements your microprocessor is composed of multiple cores. And there there is where you have the caches, second level and possibly third level caches. You have a NOC here. Of course, this is just a conceptual view, not a hardware structure. Okay. So you have several of those connected together somehow, let's say. And also you will have, at the software level, you will have primitives such as MPI, OpenMP that are at the very low level. They are capable of implementing a communication between the cores if necessary. Okay, when you have this chip, this is an integrated circuit, okay? you solder it on a board. You may have more than one chip, one microprocessor chip on the board. You for sure you will have onboard memory subsystem. In very high performance computers nowadays, you have HBM, so-called HBM memory technology. Otherwise, if you don't have HBM, you may have DDR that are, let's say, more conventional dynamic runs. And you have acceleration. Here I put a GPU to give you the idea, but you may have different types of accelerations. And also, I would like to say that acceleration is nowadays is also integrated in the same chip as the microprocessor, the general purpose microprocessor, as I will show you for the case of the EPI project, for example. Okay, so not only you have a GPU board connected to the motherboard of your supercomputer node, but you may have, for example, vector acceleration inside. Okay, in this case, it is not a GPU; it will be vector acceleration inside the microprocessor chips themselves. Okay, so this is a node of your supercomputer that is a board. Okay, PCB, printed circuit board. Many nodes are connected in a rack, and many racks, each of these is one of these, are connected through some dedicated networking technology, connected together, so that it is possible to implement message passing among the nodes. Okay, very simplified story, I know. Okay, but this is let's say very global picture that somehow not everyone knows, not everyone is clear. Okay. I forgot to put a picture of the very nice supercomputer that is installed at the BSc, the Mare Nostrum, but that is something like this big thing here. But I'm sure that someone in the previous lectures showed you a photograph of the Mare Nostrum supercomputer that is actually a connection of racks connected, installed in a very particular place. If you have not seen that, you may Google for Mare Nostrum BSc, and you will find a lot of pictures, nice pictures showing that. Okay, this is the general scenario. Before we take a break, I would like you to recall, to recall that every computer system performance, here we are talking about execution time, actually obeys this a very fundamental, very simple law. That is number of operations to be executed, whatever it is an operation, maybe an instruction, okay, maybe a number of pixels to be processed, whatever you have as a reference for your application execution. The number of clock cycles per operation, and that is, sorry, this is the operations, okay? Number of clock cycles per operations and the clock period. Here is where technology comes into the place. Okay, before we discuss a bit more regarding this, I would like to have 10 minutes break. If you have any questions, feel free to prepare them and then ask after the break. So it is 9:59 in my watch. We meet again at 9:10. Or anyway, 10 minutes from now. Thank you very much. we can improve dynamic power consumption. I see there is maybe a comment on the chat, but I cannot see the comment. Let me wait.
Mauro, Luca Valente asked if you can show the question again related to AMDA load.
Yes. Here it is. So you go for from a single core to a 10 core. 20% of the code of your application, of your program, can be split in 10 threads. Of course, 80% cannot. How much is the speed up? So the ratio between the old execution time and the new one. Okay, so how can we reduce the dynamic power consumption? There is an easy way. You reduce the clock frequency. That means you reduce this term here. This works. However, it will, of course, proportionally slow down your computer, your processor. This can be done in embedded systems only when you have idle periods of the operation, so that you can lower down the clock frequency. In some cases, some microprocessors even allow to stop the clock to most of the part of the microarchitecture. But it is not a solution for power efficiency. You are lowering the power consumption, but also the performance. A good news is that you may reduce the voltage, famous undervolting. Okay, this is true. However, you have some problems here. The first is may not be a problem. The first is that if you slow down, you have longer propagation delay. I'm going to show you in quantitative terms this. And therefore, if you slow down, if you lower the voltage, if you do undervolting, you have to slow down, you are forced to slow down the clock frequency. So again, you are slowing down the performance, the speed. And you are forced to do that, otherwise it doesn't work. And also you have a problem with noise. Nowadays, the internal voltage of a microprocessor is below 1 volt, depending on the technology, but anyway, it is below 1 volt. You cannot you cannot lower this so much. You cannot have a microprocessor, let's say a regular technology, commercial technology microprocessor that usually takes 0.8 volt supply. You cannot lower the voltage to 0.2, for example, and expect that everything is working, because there will be a lot of errors in the logic due to the noise margins. But of course, you can do something there. Okay, very carefully. I'm not telling that you can lower the voltage of a supercomputer system. Okay, no, that's not the case. Unless you do that on a board, and then you can maybe at design time you are experimenting undervolting, and then you port this to the system. This is much more useful in high performance computing for edge computing, for edge devices. That's where you can play a bit with the voltage. And then you come to the effective capacitance. Here, the average capacitance that is switched at each clock cycle is influenced by everything. Okay, you can change a lot regarding this by changing the software. For example, by changing the types of operations that are used, If you reduce, for example, the precision, you have learned that in previous lectures regarding artificial intelligence. You reduce the precisions of the weights in your neural network. At the power consumption level, what you do is reducing the switching capacitance. Of course, you change the microarchitecture, you will have a different switching capacitance at each clock cycles, and of course the technology. In general, the more advanced the technology, advanced means that the feature size is smaller. Smaller devices means smaller capacitances. So in absolute terms, a more advanced technology will have a lower power consumption for doing exactly the same operation. Okay, so I think everything is clear at this point. Any doubt? Great. So we talked about power efficiency. So how can we quantify? Can we quantify power efficiency with the things that we have seen? Okay, if the dynamic power consumption is the equation that we have seen, it means that the energy per cycle, you remove the division by the time in the formula, and you get that the energy per cycle is this simple expression. If you divide by the clock, again, you get the average power consumption. So, by the way, this is Joule or Joule, okay, without this. The previous one, sorry for saying these trivial things, this is watts, okay? Okay, this is the energy per cycle. What is the energy per operation? Okay, I can simply multiply by the number of cycles per operation. Okay, and therefore I have the fundamental formula here, that is the energy that I spend for executing one operation. One operation may be one instruction, one average instruction of my microprocessor, or whatever else, whatever is my reference operation. Okay, so in the end, what we have to do in order to improve the power efficiency is to minimize, possibly reduce this formula, this quantity. Observation, power efficiency, if you measure it as operations divided by the power, you come exactly to the reciprocal of this. So the famous power efficiency is nothing else but the reciprocal of the energy per operation. So the operation per watt, for example, the flops per watt power efficiency is exactly the same as saying the number of operations per joule. Okay. Okay. And finally, sorry for the computer scientists, this is very electrical engineering, let's say, unavoidable law of propagation delay. I was mentioning this. If you reduce the voltage, you have a problem with the speed of the logic. I will not show the demonstration of this, of course, but okay, there is a quantity that is very much used in microarchitecture design. It is called the Fo4 delay. Fo4 delay is a, you may say, a constant for a given technology and a given supply voltage, it is, for those who are interested, it is the delay of one inverter, one NOT gate, driving 4 of them identical. So that this delay here is what we call the Fo4 delay. It is a measure of the speed of a technology. Okay, there is a formula that can be demonstrated. This delay, T-Fo4, the Fo4, Fo4, by the way, means fan out 4. T-Fo4 is given by this technology constant multiplied by this expression here. This is again a technology parameter that is the transistor threshold voltage, and this exponent alpha is very close to 1. A little larger than 1, but very close to 1. Overall, if you have the voltage here, the voltage of your supply voltage of your microprocessor, and the delay of your logic gates inside the microprocessor, the behavior is exactly this one. It is this shape, let's say. It means that if you see, if you reduce, okay, you reduce the voltage, you have higher delay. That's why I was mentioning that. You have to lower the clock frequency if you lower the voltage. If you do undervolting, you have to lower the clock frequency. There is no other possibility. Otherwise, it will not work. Okay, finally, there is a parameter here that is simply the ratio of your minimum clock period divided by the delay T04, as you see here. Okay, this is called the so-called logic depth. If you refer to the pipeline of a microprocessor, you can imagine that as the number of logic delay of logic levels expressed as T-Fo4 delays contained in a pipeline stage between 2 registers, because in one pipeline stage you have let's say the timing space for 1 clock cycle. Okay, so a little excursus down to the electronic level. Okay, but it is important to have this clear. In general, how can we minimize this? That is, of course, power efficiency. Okay, suppose that you have done whatever you can do at the algorithmic software level in terms of yes, algorithm. You know, for artificial intelligence neural networks, so you can apply pruning. There are transformations to the matrix operations that you know probably very well from previous lectures. So you have done all the best that you can do, and you have the best technology that you may afford. Okay. So what can you do at the hardware microarchitecture level in order to improve the power efficiency? Okay, you have 3 ways. The first is you can pipeline, in particular pipelining along with voltage tuning. I'm going to show. You can parallelize. Again, in particular, parallelizing again, jointly with voltage tuning. Or you can use hardware acceleration. That is, I don't want to say the most effective, but it is nowadays let's say the new frontier because pipelining and parallelization have reached their limit. in practice. That is why, again, at the beginning, we told that vector accelerators, for example, are again developed. Okay, very quickly, we can pipeline our microarchitecture. Example, suppose you have a 3-stage pipeline. By the way, many ARM cores have only 3 pipeline stages. Okay, you have, you know, the NEC Patterson classic RISC pipeline, fetch. In this case, you have decode and execution, and here you have memory access and write back. Okay, nothing very important for now. Okay, suppose that the effective capacitance is estimated to be 36 picofarads. So you mean that I mean that from some simulation, you can estimate that at each clock cycle, on average, you switch this capacitance. Voltage is initially 1 volt. Clock period is 1 nanosecond, so 1 gigahertz operation, 1 gigahertz frequency. And CPI is 0.5. So you have a microprocessor that is capable of executing 2 instructions per cycle, a 2-way microarchitecture. Okay. If you calculate the dynamic power by means of our law, that is, I write here, this one. Oh, sorry. I was making, yes, that's it. Correct. Okay. You can get to this value here. You have 0.036 watts for this small core. Okay. And of course, the number of operations per second is 2 billions because of the clock period and the CPI. If you calculate the power efficiency, you have that you get 18 picojoule per operation. Okay, that is equivalent to the milliwatts per giga operations. Okay, what can we do? Suppose that we modify our microarchitecture. We design a new pipeline that, in this case, you see, has a shorter logic depth. Okay. Having a shorter logic depth means that, okay, the estimated effective capacitance is a bit higher. Why is it higher? Because you have more registers here. Okay, you have more pipeline registers. So you have some overhead in doing that. But the important effect is that you can lower the voltage. So having, you remember, slower gates, logic gates, but maintaining the same clock frequency. Okay, essentially because you have less logic in one clock cycle. Again, ideally, we may say that the number of instructions executed per cycle doesn't change. We will get back to this. If you make the calculation, you get to this new power consumption. Number of operations per second is the same as before. Power efficiency significantly improved, dramatically improved. Okay, so it seems to be a very good trick. And in fact, That's true. It is possible to modify the design of your microprocessor. Of course, in this case, you are supposing that you are designing the microprocessor to improve the power efficiency and find the optimal point. So why am I talking about the optimal point? Because it is not true that CPI is going to be maintained equal as in the previous microarchitecture. In general, there are a lot of reasons why the CPI degrades, because if you have more pipeline registers, the pipeline latency is higher. So, for example, the branch penalty may be higher. If you don't pipeline the memory, that is not obvious to do, the memory access latency grows. And so you are spending more clock per operations in general, more clock cycles. Okay, that is why there is a trade-off that I'm going to show in 1 second. I would like to mention one point here. There is an exception to this. Of course, as a first approximation, when you go into designing real hardware, always some problem comes out, but let's say as a macroscopic behavior, there is an exception to the fact that CPI cannot remain the same when you pipeline with a deeper pipeline. And the exception is the microarchitecture implementing interleaved multi-threading. If you have, if you interleave different threads, instructions from different threads at each clock cycle, you never have dependencies between different stages in the pipeline. And so in principle, you don't have stalls, you don't have increasing you don't have to increase the average clock cycles per instruction, because you don't stall the pipeline, even if you are a very deep pipeline. At least when this condition is maintained. The thread count should be the maximum, should be larger than the maximum stall latency in the pipeline. So for example, if you have a 4-stage pipeline and you have 4 threads that are interleaved in the pipeline, it works. You don't have to stall, never. I'm focusing on this because I will show you an example of such a microarchitecture. Okay, but in general, the truth is this. Suppose that you have initially your pipelined microprocessor core. Suppose that you have some voltage, supply voltage, and you have a way for measuring the picojoule per operation. More likely, you are going to simulate. Okay, you're going to simulate and perform power estimation. Nowadays, power estimation is relatively accurate, so you can do post-synthesis power estimation with good confidence, and you get some, some picojoule per operation that you can derive by the formulas that we have once you have the power consumption. You suppose that you change the microarchitecture. You have, as you see here, more pipeline stages. You lower the voltage because now you can lower the voltage. As I told you, you have the shorter pipeline, shorter logic depth. So you can lower the voltage. And in fact, you see that there is a gain. Okay, you are going down here. You have less energy per operation. You go down again because you are redesigning again your system Verilog or your VHDL for an even deeper pipeline, and suppose that you are obtaining even deeper, lower energy per operation. This is what we are going to experiment. Now suppose that you have an extremely deep pipeline. You come to this, you synthesize, extract the power consumption, calculate the average energy per operation, and you see that it has not improved anymore. The behavior is something like this. The reason for that is exactly what we told, that we have an additional overhead in the average clock cycle count per instruction, because we have increased the pipeline latency, and therefore you have more frequently, you have a stall in the pipeline. You have to stall the pipeline for some dependence. That's why you are increasing this, and the energy per operation is increasing. In addition to this, you also have the additional, let's say, parasitic switching capacitance that is affecting the total energy. So the behavior is something like this that you see here. There is an interesting point here that you see. There is a, let me delete a bit something. Interesting point. You have an optimal point, design point here. And if you try to simulate, as I told you, by power estimation, extraction, you will see that the actual optimal design point is very close to the thresholds of the transistors. This value here is the transistor threshold. When you get to this is when you what you call, you may heard about that. You may have heard about that. Near threshold. Microarchitectures. Okay, when you hear about near threshold, or even in some cases sub-threshold, but I'm more interested in near threshold because they are, let's say, more realistic for practical application. Okay, when you hear, you read some articles related to near threshold architectures, it is related to this concept. So the underlying concept is this: to find the optimal design point that minimizes the energy per operation, so maximizes the power efficiency by obtaining the optimal trade-off between the voltage reduction and the increase in the clock cycle count per operation. Any question here? Please turn on your microphone if you want. Okay, great. Before having the next break, I will consider, okay, just a note regarding the leakage. As I told you, oh, there are electronics engineers here. They will tell me, but you have static power. You don't have only dynamic power, that is this one. You also have static power, that is the leakage due to the leakage currents that you have in the silicon. Yes. I can tell you that it will, of course, affect the picture, but it will not affect the behavior. So it will be, again, the same shape, and this can be demonstrated. Okay, before the break, as I told you, I would like to consider parallelism as an alternative to pipelining. I told you, you have pipelining. For power efficiency, you may have parallelism. For example, consider again the same example as before. Okay, that's the reason why I was introducing this. Consider you have an initial core, this one, okay, capable of 2 operations per cycle, and you pass to a multi-core CPU that is capable of 2 times m, where m is the number of cores. Okay, in this case it is 10. 2 times m operations per cycle. Again, you know, there is the Untitled law. What does it mean? That actually only a fraction, that we may say a fraction x of the program code, can be split into m threads. Let's assume that we can do it. Okay, so we port our program from a single core to a multi-core. And let's see what happens to the power efficiency. Okay, for 1 minus x multiplied n is the total, right? Instructions, the average energy doesn't change. It is, again, the previous formula here. For the instructions that are actually split into m threads, of course, the CPI is ideally reduced by a factor of m, but you have at least m times the switching capacitance, because you don't have 1 core, you have 10 of them. Okay, you have 10 of them. Everyone is switching at each clock cycle, so the average switching capacitance is multiplied by m. And therefore, it is easy to see that the result doesn't change. Okay, the total energy per operation doesn't change. So apparently we have not improved anything here. However, there is a possibility. You can do undervolting. You can trade off performance gain for power. Recall, I will try to introduce an example, and I would like you to try to solve it for those who want, of course, and then we can discuss later on. Recall that you have this formula here. Okay, you don't have to use it. Okay, you simply know that you have this behavior here. Okay, it means that you have you can reduce the voltage. That is reducing also the clock frequency, but you can maintain the same throughput thanks to the parallelism. This is the procedure. Try to find the new clock cycle such that the total execution time remains the same as the original one. I will tell you, you have to apply the formula of the total execution time, the one that we showed at the very beginning of this lecture. Then, by using this graph here, you can see which reduction in the voltage you can afford corresponding to the new clock cycle. So, for example, the new clock cycle is a certain amount of times longer, and therefore you can reduce the voltage. Okay, from let's say from here. Suppose you start from here and you get here. You have longer delay. It means longer clock cycle, but considerably reduced voltage. And then when you have the voltage, you can apply the formula for power efficiency. Try this for x equal to 0.2 and m is 4. And again, please consider that the email address here is not correct. Okay, it is the one with the dot. You may try to solve this exercise if you want and see what is going on. Okay, I think it is time to have a 10 minutes break again. I am open to any question after the break, of course. Hello, everyone. Can you hear me?
Yes.
Okay. So I'm going to share the screen. Any questions in the meantime? Okay. So just to conclude our discussion regarding parallelism for power efficiency, okay, of course, you have to consider that it is not true, similarly to pipelining, okay? It is not true that for a multi-core, for the multi-core architecture and for the part of the code that is executed in parallel on the multiple cores, it is not true that the new average cycle count per instruction is simply divided by the number of cores. It is well known, and you probably know better than me, that there is an overhead due to the communications among the cores, so that in practice, let's say the actual improvement number of instruction per cycle, let's say in this case, has this shape here. It means the number of cores that you are used, actually, that you are splitting your code, actually has a maximum efficiency. In this case, we mean by efficiency, we mean simply number of instructions per cycle executed. Because if you have too many cores, then the overhead of communication is affecting the performance, and you are losing, and actually we are losing the advantage. And anyway, it is almost never possible that you have exactly an ideal speed up like this, okay? In addition to this, I'm referring to this formula. The switching capacitance is not simply m times the original switching capacitance of one core, because you have the switching that is related to the communication through the network on chip to the NOC. And so you have an additional switching capacitance as well, not only an additional average clock cycle per instruction. So the ideal result that we were looking at is actually affected in practice by this phenomena, and we have to consider them in our model if we want to have an accurate prediction. Okay. Finally, for both pipelining and parallelism, in general, any approach that employs voltage reduction, undervolting, you have to be careful, because you have the noise. You have to guarantee the necessary noise margins. So you cannot think that you can lower the voltage as much as you want. Okay, depends on the technology that you have. Okay. In practice, if you look at the let's say the scenario or regarding energy efficiency or power efficiency in the microprocessor market, what you see is that in general, the lower efficiency is characterized. Is present in those microprocessors which are more general purpose. This is something that doesn't surprise. Okay, in DSPs, that is microprocessors that are specialized for some particular application programs, that is, of course, digital signal processing, you have a gain in power efficiency, and finally you get the maximum let's say, possible power efficiency if you have dedicated hardware that is executing some special tasks. This is what we call hardware accelerators. Okay, there is a famous, and in particular, I am referring to vector computing here. There is a famous picture that was shown some years ago in a conference. That is this one. You see, this is the little application that was implemented in different ways. Totally dedicated ASIC, so totally hardware, okay? Pure hardware implementation on integrated circuits. The same implemented on FPGA, okay? The same implemented as assembly program in ARM microprocessor. The same implemented as assembly program in a much more complex and higher performance, of course, Pentium 3 assembly language, Pentium 3 processor. The same compiled from C language and the same compiled from Java. Okay, what you have is that the energy efficiency, in this case, the energy efficiency, power efficiency was measured as the gigabit per second that were achieved by the execution divided by the power, the watts. You see that there is an enormous difference between the most general purpose implementation and the most specialized one. So that is the reason, let's say that, not the reason, but the demonstration that having a hardware block that is executing some particular application, some particular computation, okay, in your microprocessor is extremely powerful for improving the power efficiency. Referring to the concepts that we have analyzed in the previous 2 hours, you may try to think a bit and think why a dedicated hardware accelerator. So for example, suppose that you have a hardware block that is capable of executing, I don't know, dot product, okay, between 2 vectors. It is executed directly by this block here, okay, vector dot product. So you may try to think a bit, why does this improve power efficiency? Remember that we have these components that we can operate on. And the answer is that potentially you can actually operate on all of them if you have a hardware accelerator block in your microarchitecture. You may try to figure out in detail and send me the answers if you want. Okay, again, this is wrong. This is wrong. Okay, I'm open to discussion on this later on. But I would like you to reflect a bit, to think a bit about this. Okay. Okay. Regarding hardware accelerators, for example, hardware accelerators for vector computing, there are different approaches. Of course, it is always an approximation to classify approaches in, let's say, static boundaries among them. However, broadly speaking, one approach is to have instruction mapped acceleration. This is all sometimes called tightly coupled. Recently, another word that has been resumed from the past for expressing this is coprocessor. This is a coprocessor, especially in RISC-V systems. This is a word that has been resumed from the past to express this concept. So the point is, the hardware accelerator, in this case a coprocessor, is actually directly driven by the instruction fetch of the core. At a certain point, the core will fetch an instruction that is an instruction that can be executed directly by the hardware accelerator. So it will pass the instruction to the accelerator directly. Okay, after the instruction has been executed, possibly by direct interaction with the data memory by the hardware accelerator, execution is resumed by the core, or maybe anyway the execution, if there is some kind of superscalar execution, maybe that while the accelerator is executing the accelerated instruction, then at the same time the core is executing some other instructions. Okay, that is possible. Okay, depends on how the core is designed, if it is supporting superscalar execution or not. So the classical example is a vector instruction. Okay, as I was mentioning before, the core here fetches, for example, a dot product instruction. Okay, the dot p instruction. The microarchitecture of the core is designed in such a way that the dot product vector instruction is recognized. It is passed to the hardware accelerator, that is the vector coprocessor in this case, and executed directly by that dedicated unit. Okay, this is one approach. Another approach is based on so-called memory mapping. I am sure that Luca Benini showed you this approach in one of the solutions that he proposed. Sometimes it is called loosely coupled, but not necessarily. In this approach, actually, the core is not directly connected by some control logic to the hardware accelerator, or at least not as in the previous approach, so that an instruction is directly passed. What happens is that the core actually controls the hardware accelerator by means of memory instructions. Actually, it will write commands for the hardware accelerator by looking at them, at the commands, as if they are memory locations. So we may say that some region of the memory space is dedicated to the commands of the hardware accelerator. In this case, of course, the interaction is slower. It means that for starting the hardware accelerator requires some more clock cycles than simply having to pass an instruction and having that executed. So this is usually the case, that the hardware accelerator executes relatively complex computation kernels, not a simple vector instruction. Like, for example, you may have a convolution here, directly executed, entirely executed by the hardware accelerator. Okay, so you write the command through from the core point of view, it is just a memory store operation. You write the command, of course, you write the data into the proper space if it is necessary. It depends on the, of course, the design of the accelerator itself. And the accelerator starts executing, for example, the convolution. It may access the memory directly, the data memory, of course. And after the convolution has been executed, it will inform the core by means of some flag memory location where the core can see that the operations has been completed. Okay, different approach. In this case, the hardware accelerator, I mean the first one, the hardware accelerator can execute relatively simpler tasks, like as example, vector dot product. Okay, not an entire convolution. It is not the case that you have an instruction in the core that is fetched from the memory, of course, from the program memory. You have an instruction that is an instruction for executing a convolution. It is very unlikely that you have such an instruction in an instruction set, but you may have vector instructions. Okay, and it is the case of vector processors. Okay, from a hardware point of view, microarchitecture point of view, you may have accelerators that are dedicated to a core. So each core in the microarchitecture has its own accelerator. This is the case that we are going to see in a few minutes. So, for example, each pair, okay, of core and accelerator implements a vector processor, okay? Or maybe that you have cores that can individually access one accelerator or the other accelerator. Okay, in this case, you don't have an accelerator that is dedicated to one core. And finally, there is also an approach that we will not see in detail, but in principle, I want to mention it. It is so-called accelerator building blocks. It means that you don't have entire accelerator blocks, but you have some hardware blocks, which are basically functional units that can be dynamically configured by means of software instructions to implement a particular acceleration, like a vector instruction, for example. And so they can configure the ad hoc. Okay. So this is, let's say, the scenario, overall scenario of the different approaches for hardware acceleration in a microprocessor chip. All that I am talking about here is on-chip accelerator. Okay. So I'm not talking, let's say, these approaches that I am illustrating does not apply very well to an implementation where the accelerator is in a different chip. Okay, like the case for a GPU. This is something different. This is good for vector accelerations, for example. Okay, so let me change the set of slides. The first design case that I want to show you as an accelerator is something that is related. Sorry, I have to choose the right slides. Yes, here it is. Something that is related to previous lectures that you have attended. Can you see this new slide?
Yes, we can see.
Yes.
It.
Okay, great.
Yes.
As you can see, I have changed the style of the presentation because this is related to the European Processor Initiative project, and there is a strict indication of using a particular style, and in particular applying some specific statements for acknowledging the European Commission that is funding this project, this very big project. I know that you have heard about this. In particular, Professor Jesus Labarta have explained something regarding this this project, and that was related mainly to the programming paradigm and the overall performance experience, performance evaluation in the software development vehicle that have been implemented. Now, I am glad to have the possibility of showing you a bit more in the microarchitecture level of this project, the same project. So it is complementary information with respect to the previous lectures. By the way, you know that this is the timeline of the project. I'm sure that Jesus or maybe John Davis also showed something like this. What I am talking in this lecture is this thing here, the test chip regarding RISC-V EPI accelerator, so-called EPAC. Okay, that is EPI accelerator. This is the first chip that was taped out in 2021, and there will be another one much more complex than that, the first generation of general purpose processor that will be called REA, and in the future the second generation. Okay, so what I am talking about is the first achievement of the project, the first, let's say, concrete achievement. That means first silicon. And this is particularly related to the concepts that we have illustrated in the previous hours of this lecture. So, the DPI accelerator, so-called EPAC, demonstrator test chip, is composed of a microarchitecture that includes a multi-core processor. In particular, you see here, I'm referring to this picture. You see you have several scalar cores that are associated to a vector processing unit. Exactly the concept that I was mentioning a few minutes ago. So this is the case of a coprocessor, vector coprocessor, that is employed for accelerating vector computing applications. The chip also includes dedicated units that are, for sure, they have been explained by Luca Benini, the STX, which are differently from the vector acceleration. They are dedicated to artificial intelligence computing, in particular neural computing, neural networks, and they are memory mapped. So they are kind of more loosely coupled accelerators with respect to the this approach here, that is a tightly coupled vector coprocessor. Okay. Of course, everything is connected by a network on chip, so the microarchitecture is relatively complex. I think Jesus gave a short glance to this, and on the right side, on the left side here, you see there is this high-speed SerDes interface. It means this is connected to an external FPGA, because as you may see from the layout, we don't have memory controllers on this chip. The reason is that this is a demonstrator chip, including dynamic RAM, DDR memory controllers, or even HBM would be extremely expensive, and it makes no sense for a demonstrator test chip. The chip was taped out in April, and we are waiting. It is a matter of days for the first silicon samples. Okay, the target clock frequency is 1 gigahertz, and the technology is 22 nanometer FDSOI from Global Foundries. Okay, the target of the vector processor is to implement 16 double precision gigaflops per core. It means 16 double precision giga operations per cycle. 16 double precision floating point operations per cycle. Okay, we have, by the way, we have 4 cores, as you can see here, 4 vector processor cores. Each of them, including the scalar core. By the way, the scalar core is the Avispado that for sure Roger Espasa illustrated in his talk a few days ago. Okay, so what I'm going to show you is a bit how it works internally. So how does this vector processor execute vector operations internally? Okay, internally, by the way, this is the NOC with the low level 2 caches, okay? Here you have the STX units that are specialized for artificial intelligence applications, in particular convolutions and similar computation kernels. And there is also a unit that I forgot to mention. It is a variable precision unit that is capable of supporting arithmetic precision, which is much larger than usual. This is, for example, cryptographic application are going to use this. And then we come to the vector processor. So we have in the concept of the architecture is up to 8 vector processors. In the present implementation, present silicon tape out, we have 4 cores. We have 4 of them. As you can see, internally, this is the Avispado scalar core. The Avispado scalar core has its own first level cache. I will not go through this because for sure you already heard about that in previous presentation. What we are more interested is this part here, that is actually the vector coprocessor. Okay, the vector coprocessor is implemented as 8 vector lanes. These are 8. Okay, a vector lane includes a portion of the vector register file, not an entire register file, portion of the vector register file, along with the arithmetic functional units that, of course, execute the operations on the vector elements, supporting double precision, single precision floating point, and integer precision, integer formats with different precisions from 64 bits down to 8 bits. So let's look at one vector processing unit. So I go back 1 second. So I'm going to show in detail the microarchitecture of this here, the 8 vector lanes. Okay, the microarchitecture looks like this. As I was mentioning, you have the 8 lanes here. Okay, so this is one lane, this is another lane, and so on. Each lane, as I was saying, includes one section of the vector register file. It means that the whole vector register file is distributed among the lanes. In particular, maybe this is a bit too much in detail, but for example, the first element of a vector is stored here, the second element is here, the third is here, and so on. And then, of course, it will rotate and go back to the first. Okay, there are some considerations behind that that led us to implement this kind of microarchitecture organization. You have the functional units, and of course you have some finite state machines that implement the control of the operation. On the top of the picture, you see there is this store management unit here, as the name suggests. It is in charge of receiving data from the vector register file and storing them to the memory. However, in this microprocessor, the memory is not directly accessed by the vector unit. The data actually go to the Avispado scalar core here. Okay, so they go through the interface between the scalar core and the vector core. It does not go directly to the memory. This is part of what is called the OVI, Open Vector Interface, that for sure Roger Espada from Semidynamics presented you a few days ago. Of course, we also implement load operations. So receiving data from the memory. This is a bit complex, more complex than storing, because when you receive data from the memory, I mean, for example, you load a vector. Okay, you load a vector from the memory. Since you have caches down to the memory hierarchy, it is not guaranteed that the elements arrive in the order that we expect, just one after the other. Okay. Therefore, we had to implement a data reordering unit here that is actually internally including several buffers. Those buffers are filled with data in the proper order while they arrive from the memory. Then we have a so-called load buffering unit. This is a bit different because we may have more than one load operation in flight. And therefore, there is one load buffer dedicated to, let's say, to each line of the vector that is being prepared to be stored in the register file. And finally, when a row of the vector is ready, it is stored in one clock cycle into the vector register file. Okay, so there is a lot of work done before having the possibility of writing the data coming from the memory directly to the vector register file. This is a problem that any vector processor has. Okay, so final component of the picture is this part here at the bottom. I will not show this in detail. This is let's say the interconnect between the lanes. Why do we need? In a normal arithmetic operations, we don't need any communication between among the lanes because reading the operands of an addition, for example, the elements of an addition, and writing the destination element may happen all inside the same section of the register file. This is let's say a normal way of operating, but there are instructions that, as many of you know, involve the movement of vector elements among the lanes, meaning that, for example, sliding operations. Okay, you have to slide the vector elements in the position to change the positions of the elements within the array. That implies communicating between the lanes. There is an interconnect that is a ring. In reality, it is a double ring topology that implements this communication in this microarchitecture. Okay, instructions are received from the Avispado core here. There are some, sorry. And there are some preliminary steps. Some of the instructions actually are unpacked in simpler operations in some cases. We apply vector instruction renaming. We have register renaming. In practice, we have 40 physical registers, while there are 32 physical logical registers in the vector specification of RISC-V. And okay, and we have an instruction queue here. So in the instructions are passed to the lanes once they are ready for execution. I assume that you are familiar with the vector in extension of the RISC-V instruction set, so I will not go. So I will go quickly here. As I mentioned, you have 32 logical vector registers. That means that you have, for example, this is one vector registers. You have 32 of them, and the length is up to this VL max. VL max in our microarchitecture is 256 elements. So we are targeting long vectors. As probably Jesus Labarta told you, this is a kind of philosophy of this microarchitecture. Okay, then you have some specialized vector control and status registers. You have, for example, the size of one element that may be 32 bits, 64 bits, or so on. The actual vector length that is applied to the operations, because we have a maximum vector length of 256 elements, but we may have a different vector length that is actually applied in executing the instructions. And then, okay, some other that I don't want to spend time on because it is not the case, since you are probably more familiar than me with the software level of vector programming. Okay. One feature of this architecture is that it includes, of course, like many instruction sets for vector processing, different kind of load and stores, vector load and stores, in particular non-strided as well as strided, so that you don't have just vector elements coming one after the other, but with intervals within them, and also the very complex operations that are gathers and scatters, where you have indexed loads and indexed stores. So the index of one element that is being loaded on stored are actually elements of another vector. Okay, so example of vector instructions that are supported by this RISC-V vector extension, the classical arithmetic operations. Some control instructions, for example, to set the vector length and the element width, and the load and the stores. Okay. Okay, what is more interesting for us now is to discuss the microarchitecture of the vector lane. I would like to go back a few slides because I want to to show you what I am referring to. Let me delete 1 second here. Okay, I am referring to what, let me change the color. I am referring to one lane. Okay, just one lane. So let's look inside here. Here we are. Okay, this is the portion of the register file. This is implemented by 5 banks of static RAM, static memory. And it is a single ported memory. The reason for that, for this choice, is that in the current technology, in order to reach 1 gigahertz frequency, it is not feasible to have multi-ported memories. So we were forced to use a single ported memory and to use this particular organization. Okay, you see there are 5 banks. Okay, suppose, okay, by the way, on the top here, you have the load buffer for data coming from the memory, possibly. And here is a write-back buffer that is used for as a buffer for the results of arithmetic operations. Here you have the functional unit. For example, this may be a floating point unit, okay? It is pipeline. This is the reason why you see these bars, vertical bars here. And then you have these buffers here, buffer A, buffer B, buffer C, as well as the memory store buffer for storing data to the memory. Buffers A, B, and C, they are data buffers for arithmetic operations. And I'm going to show you how they work. Suppose that we have to execute this instruction here. It is simply a vector addition. So we are going to add the vector 1 and 2 and, okay, sorry. This is a particular vector, but anyway, we have to write into a destination register. I use these colors here. The 2 operands are represented with this blue and red and green input operands of the instruction, and destination is in red. Okay, here you have the pseudocode that is actually modeling what the instruction must do. In practice, it is an element-wise addition. Okay, so we started from having, as you see from the picture, we started from having the source vectors in the register banks. As I told you, for example, this may be element 0, this is element 1, this is element 2, 3, 4, so on. And then you go for the next lane. Okay. And after you will get 40 here, number 40, 41, because you have 8 lanes, each of them 5 banks. Okay. Okay, how it works. So first clock cycle, you see, I am sorry, let me delete all the things here. You see, I am in the first clock cycle, I am loading buffer A. In a single cycle, I am reading 5 elements from the first source operand, source vector. Okay. In the next clock cycle, I read 5 elements in the buffer B. In the next clock cycle, I start doing the operation. You see, there are, if you look at in this part of the picture, you see there are elements that start moving to the functional unit. Next clock cycle again, I am gradually taking elements from the buffer A and B, passing them to the functional unit so that the result is computed in pipeline. This is the first, this one here is the first element of the destination. In subsequent clock cycle, what we do is that we pass the element that are computed, you see, from the functional unit to the write-back buffer. So we are gradually filling the write-back buffer here. And in the subsequent clock cycle, in a single cycle, we load, we write back, let's say, we write the result into the destination vector in the register file. Okay. Of course, this is the principle. I may have said that, I go back a bit. Okay, while this is being executed, new values are filled, are loaded into the buffer A and B for going on with the subsequent elements of the vector. Okay, so everything is perfectly pipelined. Okay. An additional information is that there are cycles in which no elements is written from the write-back buffer to the register file, and no elements is read from the register file. And so we can use this clock cycle, as you can see here, with these arrows here, for loading element values that are coming from the memory. Different instruction, okay? There is a let's say, a load vector instruction that is going in parallel with the execution of the arithmetic instruction. This is organized in a, let's say, perfectly synchronized way. I may say that the overall operation goes through 5 states. We may say loading a buffer A, loading buffer B. In case there is a 3 operand operation, we have also buffer C. You know that there are operations, vector operations with 3 operands, like a vector fused multiply add. Then we have a state for reading something from the memory, and then we have a state for writing back, and then we go back here. So the state machine that is controlling this operation continuously go through this sequence of states. And in this way, it is possible to maintain the pipeline of the functional unit always filled with data. This may be not completely evident, but if you try to draw a timing diagram of this, you will see that this is possible. I can show you, before taking the next break, I can show you what is the expected peak performance. Okay, if you look at this picture, you see that, for example, if I have a vector that may be surprisingly composed of only 1 element, okay, in that case, the architecture is very inefficient. Because anyway, I will employ, even if the pipeline is filled, completely filled, I will employ 5 cycles for obtaining the result. The throughput that I can expect, I can show you with another slide. The throughput that I can expect from this organization is, sorry, I have to share this slide here, is something like this. This is the vector length. on the horizontal axis, the number of elements. Okay, so we go up to, as you can see, 256 elements. If I have very short vectors, the number of operations per cycles, I mean, when I refer to operations, I mean operations on elements. For example, addition of 2 elements, floating point addition, okay, is very low. It will get the peak when the vector length is a multiple of 40 elements. Okay, and that is because we have 8 lanes, each of them 5 banks. So if you think a bit of the operations that I described, you will see that you reach the peak performance, meaning that there is no idle cycle in the pipeline. There is no bubble in the pipeline for those particular cases when the vector length is a multiple of 40 elements. But the point is that in our microarchitecture, we are targeting applications with very long vectors. So we are always here in the applications that we are targeting. That is, the peak performance is to have, in a single cycle, 8 element operations, 8 operations on vector elements per single cycle. If this is a fused multiply add, you have 2 floating points operation in it, and therefore it will the peak performance will translate into 16 flop per cycle. That is the peak performance. Okay. So I think I will conclude this part, and we can take a 10 minutes break again. Any questions is welcome, of course. Questions? So I assume everything is clear with the microarchitecture of the EPI vector accelerator. Okay. So let's go on. Let me share the screen 1 second. Okay, sorry. I see there is a question in the chat. It is an interesting question. Is there any reason for using 5 register file banks in each lane? Okay. We thought about that a lot. It is not a choice that is something written in the stone. Actually, I can tell you that is related to the fact of having those 5 phases in instruction processing, meaning reading operand A, operand B, operand C, possibly having a cycle for memory load and writing back. So we have for each of those phases, which corresponds to 1 clock cycle, we have an access to the register file. Okay, and so in order to have to start again the sequence, in order to start again the sequence from the first of the 5 stage, you have to read 5 elements from the register file. I don't know if it is clear enough, but the reason is related to that. So to having a let's say always a full pipeline while having these 5 elements, 5 phases in the instruction processing. It doesn't mean it is the only possible choice. I can tell you we are considering for next versions to have more than 5 register file banks. This would mean that we are going to possibly not having a 100% utilization of the register file, but that may be not a very bad choice anyway. So it is something that can be discussed for further versions of the design. There is another question in the chat. In which phase do you do memory store? In the same cycle dedicated to memory load. So you cannot do it presently. You cannot do you cannot load the data and store data from and to the memory in the same clock cycle. Okay. So I think we can go on. We don't have so much time. So we have seen a machine that is dedicated to very high performance computing. Okay. By the way, a machine that is targeting the same philosophy of very long vectors is the Aurora machine, the Aurora supercomputer. You may look at the on the internet. That is totally different architecture and has nothing to do with the EPI processor, but shares the same philosophy of having very long, targeting very long vector length. Okay, here we are. I'm going to share this set of slides here. So we have seen a machine that is devoted to very high performance computing. Now, so when I say very high performance computing, I'm thinking of a very large computer system, okay, like the Mare Nostrum or many others. What I am looking at now is the extreme opposite edge of the picture, okay, the IoT devices, okay, edge computing, still having vector acceleration in order to improve power efficiency and performance, of course. By the way, there are other examples of vector processors dedicated to edge computing. One that I want to mention that I will not cover, but I want to mention is the ARA. ARA is developed by ETH Zurich, and another one is Wacha, developed by Berkeley. Okay, in fact, Wacha is not explicitly for edge computing, but it is anyway a different example of the vector processor that you may take a look at if you are interested. Okay. The microarchitecture that I'm going to show you is the Clasidra Microarchitecture. Clasidra is a family of processor core that we designed in the Digital System Lab of Sapienza University. The people that I showed you at the beginning of this presentation, of this lecture. It was presented in a number of places, including some journal articles recently. I will give some references at the end, and in particular in the RISC-V Summit in December 2020. Okay, the features of the Clasidra family is that it is fully compliant with RISC-V architecture, instruction set specification. A particular feature is that it implements interleaved multi-threaded execution. You remember I mentioned the multi-threading as one possibility of improving power efficiency and performance also. This is different approach than simultaneous multi-threading, as I'm going to show you in a few seconds. And also it supports hardware acceleration. So these are the two features that we are going to emphasize in this discussion that we are going to have in the next few minutes, okay? We also have a runtime, very simple runtime software library. The core has been presently synthesized in a number of FPGA devices. I said the core, but I would say the cores, because it is not actually one microprocessor core, but it is a family of cores that can be parameterized. So you change the parameters of the microarchitecture and you can synthesize a different microprocessor on the device, on the FPGA. This is interesting in the future for reconfigurable and automatically reconfigurable computing. That is one of the field of research that I'm working on. We are also developing a silicon implementation that is going to be taped out next year. But it will be anyway not a product, but an academic research prototype. Okay, what are the targets? The targets are the things that we are talking about: edge computing, so small devices in an embedded application domain. And another field that I will not focus on is space avionic onboard processors. In fact, we have one satellite that was launched on March, if I remember well, March 2021. It has one of our Clasidra microprocessor core on board. It may be the first RISC-V microprocessor in the space. I'm not sure of that, but for sure one of the first. Okay, by the way, it is developed in VHDL, not in System Verilog. We have nothing against System Verilog, but and we do have System Verilog IPs in the platform architecture around the core. It is fully compatible, but in my experience, VHDL is a much more robust language, and so that is why we like VHDL, in particular for space application. VHDL is particularly preferred by the space agencies. Okay, just very few information about what we are talking about. So we started from the Palpino platform. You may have heard about that. That was developed by Luca Benini's group. You have a microprocessor core inside here. It is a microcontroller platform with different several peripherals, instruction and data memories included. What we designed is the microprocessor core. So we started with a basic, a very basic core that is this one here, that is even not available anymore at the moment because it is obsolete. We introduced the multi-threading with the T0 cores, and then we developed the T1 subfamily that is incorporating vector processing here. And the other one is the F0 subfamily that is incorporating fault-tolerant features, and this is the one that is targeting space applications. Okay, we are not going to talk about that. We are going to talk about T1. At the moment, T0, that is the one that is not accelerated, but still has the multi-threading support. It is obtained by synthesizing the T1 with particular configuration of the parameters in the RTL design. We support integer operations with also some partial support for atomic operations because we have multi-threading. And for the vector extension, we developed our own vector extension. So we have not followed the official RISC-V vector extension, because we have a different paradigm that I'm going to show you. And because for the particular, let's say, very extreme edge application domain that we are targeting, we believe that the whole extension, vector extension of the official RISC-V specification is, let's say, too much. It is very heavy instruction extension. If you have studied it, it is a very complex set of instructions and architecture features that are okay for complex processors like the one that I showed you for the EPI project, but not at the moment in our application of interest. So about multi-threading, the logical model that we have, consider that this is the pipeline of the process of this instruction processing pipeline, and suppose that you have the hardware threads identified by different colors. You see that you have a different color in each stage of the pipeline. In this way, it means that there is an instruction for the green thread in the first stage, an instruction from the blue thread in the second stage, an instruction from the red thread in the third stage. In this way, you guarantee that there cannot be any dependency, data dependency or branch dependency between instructions in the pipeline, because they are from different threads. By definition, there is no dependency. No direct dependency. There can be dependency only by means of accessing shared memory. And this is, let's say, a software level mechanism of interaction. Okay, so this is the basic concept. Let me look at the hardware microarchitecture. Okay, this is what we call the T03. 3 means that there must be at least 3 threads in the pipeline in order for the pipeline to properly work. I see there is a message on the chat. Let me close for 1 second here. Why do we need multi-threading on a microcontroller? Okay, for example, you may have a sensor node that is processing multiple images taken from the environment at the same time. It takes 3 pictures and it processes them in 3 different threads. Or maybe you may have one thread that is processing an audio stream taken from the environment and another thread that is processing video information. So there is this possibility, and it is a particular application domain that we are looking at. Okay. 1 second. There is one person that wants to be admitted. Here you are. Okay. Okay, T03. By the way, the pipeline in this case is vertical. Okay. As you can see here, there is nothing but a classic RISC pipeline here, except for the fact that you have 3 program counters, because we have 3 threads in this microarchitecture case. And of course, you need 1 program counter per thread. Okay, each thread must have its own program counter by definition, and also its own register file for data registers, and its own control and status registers. So the only thing that is splitted in multiple replicas is the program counter, the register file, and the control status registers in this microarchitecture. And here you don't have any acceleration, don't have any vector acceleration, okay? The vector acceleration we introduced as an extension of this microarchitecture that I'm going to show you here. Okay, First of all, you see that in the execution stage, we have now three units, let's say, general purpose execution unit that is executing most of the scalar operations, a load store unit that takes care, of course, of the memory accesses, and a specialized unit here. This, we may say, referring to the previous concepts that we have described in the lecture, it is the vector processing unit. It is the vector coprocessor. Okay. This MFU, that means multi-purpose functional unit, is equipped with this thing here that is called SPMI. That means scratchpad memory interface. A big difference with respect to the previous vector architecture that we are using in this microarchitecture is that we don't have a vector register file where you have a fixed number of vector registers, but we have local memories that we call scratchpad memories, in which we can store the vectors in a more flexible way. So you don't have a vector register dedicated, for example, to one vector. The number of vectors in principle can be any, provided that the space in the memory is enough. Okay, so if we go in a bit more detail inside this vector unit here, okay, on the top side, is there any question? I think someone that must can you mute the microphone, please? I don't know if Amalia can mute the microphone to someone possible.
Yes, I'm trying to identify who it is.
Okay.
Just 1 second.
Okay, I will go on, no problem. Sorry, maybe I lost the screen sharing here. Here we are. Okay, so I was describing, here we have the functional units. Okay, since we are executing vector operations, we are going to repeatedly operate on the vector elements, and so we need a support for hardware loops inside. The actual functional units are this part. As you can see, it includes addition, subtraction, shift, multiplication, accumulation, and compare. They can be, okay, depending on the particular configuration of the microarchitecture, they can be used separately and concurrently or not. Okay, I will show you in the next slide. And on the bottom part, you have the actual scratchpad memories. Okay, what I would like to point out here is that those red numbers that you see is they are actually the parameters that you can change when you synthesize the microarchitecture. So, for example, the number of scratchpad memories is a parameter. You can have 1, 2, 3, 4, usually more than 2 scratchpad memories in your microarchitecture. The number D is actually expressing data level parallelism, and it corresponds to the banks of the scratchpad memories as well as to the number of parallel functional units. I mean parallelism in this way. Okay, so for example, you have not one comparator, but you have 4 comparators if D is equal to 4. This is for SIMD fashion of operation. Okay. Similarly, you have this parameter F. This is a bit different. It expresses the possibility of allocating only one accelerator for the 3 threads. Remember, a shared accelerator in this case, or having one accelerator dedicated to each thread. Of course, the hardware will change, so it will be larger if we have 3 accelerators instead of 1. For those of you who are more on the software side, this is the memory map. Actually, it is totally compatible with the Palpino and the Pulp memory map. You have the program memory here on the top. It is a very small one because we expect to execute very small applications in terms of the image of the binary program. In this version that I'm showing here, we have 1 megabyte of RAM, but we can have less than that usually. Interestingly, inside the data memory, we have a space that is dedicated to the stack of the threads. Each thread, each hardware thread will have its own stack. And also there is a shared space that is available for communication, shared memory communication among the threads. At the bottom here, you see the peripherals that are mapped into a memory space. Okay, this long list here is our vector extension. If you look at the vector extension of the RISC-V official, let's say, vector extension of the RISC-V specification, it is 100 pages, even more. In our case, we have much simpler thing. I will not go through in detail, but it is very easy to look at it. If you take 1 second, okay, here you have the assembly. Here you have the mapping at C language level. All the assembly instruction, vector assembly instructions are mapped onto an intrinsic function that you can use very freely in your C program, and it is very straightforward, compiled by the compiler into the assembly vector instruction and into the binary code. So, for example, you have vector load and store. This is very similar to a memcopy operation. It is actually used to load portion of vectors into the scratch pads, from the main memory into the scratch pads, and the opposite, and vice versa. It corresponds to load something into the vector registers in a vector-based, in a register file-based microarchitecture. Then we have plenty of fundamental arithmetic operations among vectors and among scalars and vectors. The interesting point here is that all of the assembly vector instructions have regular scalar registers as the operands, and the register are supposed to contain addresses that point into the scratchpad memories. That is why if you look at the C intrinsic function, for example, this one, that is a vector multiplication, you see that it takes pointers as the arguments, and these pointers actually are supposed to point into the scratchpad memory region. I don't know if I told that, but the scratchpad memory region is here in the memory space. By moving data into this region, you are actually physically moving data into the scratchpad memories that are the local memories of the accelerator. Okay, So we have this list of operations. If you are interested, you can go through. You have also some something that is related to artificial intelligence applications, the ReLU operation. We have also some control operations that are related to setting the vector length and the vector size, vector element size. Okay. So I can show you some performance profiling of this microarchitecture. We made a lot of work. We synthesized a lot of configurations. By the way, I am afraid that there was one slide that I wanted to show you, but I don't see the picture here. Okay, I can summarize. Yes, I can summarize easily. Okay. By changing the parameters of the microarchitecture, of the accelerator microarchitecture, you remember those D, F, N, and so on that I showed you in the microarchitecture picture, you can actually obtain different ways of operations of the microarchitecture, from single instruction, single data, to SIMD operation, pure SIMD operation, that is data parallel operation, as you know, as a MIMD plus SIMD, meaning that you have multiple threads and each of them has its own accelerator, and its own accelerator is based on a data parallel execution inside. And also we have a different configuration that we can build, that is we consider it as a heterogeneous SIMD, meaning that we are not, sorry, not heterogeneous SIMD, but heterogeneous acceleration execution, because there is only one accelerator, not for the shared among the threads, but the single functional units inside the accelerator, you remember addition, multiplication, comparison, and so on, they can be used in parallel by different threads. So it is a heterogeneous parallel execution. All these different execution schemes you can obtain by changing the parameters of the microarchitecture before the synthesis. This is why I am going to show you a performance profiling that is covering a lot of configurations. Okay, what is the workload that we experimented? The workload that I show you was composed by convolution, in particular with the 3x3 filter size and different matrix sizes. The FFT, fast Fourier transform, that may be useful for several application domains like audio processing, for example, and matrix multiplication, that is, of course, useful in a lot of fields, including neural networks for fully connected layers, as you know very well. We experimented both a homogeneous workload. So, for example, you have 3 threads running the same applications, of course, on different data. So, for example, you perform a 2D convolution on 3 different images, okay? And you have 3 threads running them. Or we also considered a composite workload where you have 3 threads that are each executing a different computation, convolution, Fourier transform, and matrix multiplication. Okay. Let's look at the performance results. Okay. Of course, there is a lot of numbers here, so you can take your time to look at, but I would like to point out some of the key features here. As you can see, the clock frequency that you can reach, okay, depends on the type of microarchitecture that you are implementing in your vector accelerator. Okay, this doesn't mean that the story finishes here. In general, the more complex the architecture, for example, this one with 8 SIMD degree, so you have 8 operations per cycle on the data, and also with MIMD operation, that is each thread has its own accelerator dedicated. Okay, of course, this is the one that is the slowest for the clock frequency because it is the most complex one. Interestingly, we put here some reference for comparison. Let me delete something. Okay, you see that the T0, Clasidra T0, which is interleaved multi-threading without any acceleration, is very fast as a clock frequency. And interestingly, it is much faster than the risky and zero risky cores, which are the original cores of the Palpino platform. The reason for that is that we use interleaved multi-threading, and so we get rid of any hardware control in the pipeline. There is no other reason. Oh, by the way, I forgot to mention that we are using FPGA implementation in this analysis. Okay, the FPGA, the target FPGA was an Ultra Xilinx, I believe UltraSpark, if I don't remember wrong. What is more interesting is looking at the cycle count, total cycle count per computation kernel. And you see that we go from relatively high cycle count to an extremely low cycle count for the heaviest acceleration. Okay. Interestingly, the applications that get the greater advantages, of course, are those that can be better mapped into a vector acceleration. For example, the FFT, of course, is gaining, but not so much as a matrix multiplication or convolution. This is a very interesting diagram. It compares a lot of different configurations of the vector acceleration. Okay, you see, for example, SIMD with the DLP degree, data level parallelism degree 2 or 4 or 8, MIMD, and so on. This is the heterogeneous execution scheme. And the reference here is the zero risky core. Zero risky is a very simple core that we take as a reference, let's say, for normalizing the results. Okay, and this is execution time. So this is not cycle count. This is, you remember, execution time, total operations, cycle per instruction, per operations, clock. Okay, and this is directly measured by simulation, by execution on the FPGA. So what you see here is that the best performing microarchitectures for the convolution, okay, is this and this. It corresponds to the largest parallelism in the accelerator, but interestingly, there is little difference between having a dedicated accelerator per each thread, or having a shared accelerator. So the microarchitecture is somehow capable of taking advantage of a single accelerator in a very good way. It is almost the same performance. It is 17 times faster than the zero risky simple core. Okay. So this is an interesting result. Another interesting result is that if you look at the composite workload, well, in this case, the largest data level parallelism is not the one that reaches the highest, let's say, the best performance, but it is a bit of compromise. It is 4 operations per cycle in the acceleration unit. And this is because the composite workload is not simply matrix operation, but it involves other kind of computations. We can take a look at energy efficiency here. Okay, in this diagram, lower is better. Okay. Again, in this case, the results are expressed as energy per algorithmic operation. So you take the total energy, you divide by the number of addition and multiplications that you have in your convolution operation, for example, and you have the energy per algorithmic operation. And again, it is normalized to the zero risky performance. You see that the lower, again, the lower energy per operation is obtained here by this microarchitectures, which are not the one with the highest data level parallelism. Okay, and another thing is that if you look at the pure SIMD, also in the previous picture, where you don't, you only have data level parallelism, and you don't have MIMD operation, so you don't exploit the multiple threads. That is the case where you are not so efficient as when you are exploiting multi-threading also. Okay, just a very quick look. If we consider also larger convolution filters, larger than 3 by 3, the trend is more or less maintained. Okay, so you always have an improvement with respect, a significant improvement, up to 35 times speed up with respect to the basic zero risky core. These are some considerations. So the mixed application of multi-threading and data parallel execution is the one that is the winner, is the one that allows you to have better results in terms of energy efficiency, but also on absolute performance. And what is interesting is that fully symmetric MIMD and heterogeneous MIMD. Heterogeneous MIMD is a name that we gave to the configuration where we have one accelerator shared among the different cores, give very similar results. So it seems that it is not always necessary, at least, to have one accelerator dedicated to one core, to one thread. And the other things I have already discussed. One thing that, if you go through the previous slides, you may take a look at, is that even without hardware acceleration, the fact that you have interleaved multi-threading is improving the energy efficiency, power efficiency, energy efficiency, with respect to a more traditional single thread RISC pipeline. Okay, before closing the lecture and asking for some questions, I would like to propose you a design exercise that you may, if you are interested, you may look at in the slides and try the solution. You have always heard about artificial intelligence, convolutions, neural networks, and so on. In this case, we do something much simpler. It is an edge detection algorithm, and the algorithm is extremely similar. We scan the image horizontally, and we find where there is a difference in the brightness. So we decide that there is an edge there, and so we plot one pixel in the destination image. Okay, the thing works. This is something that my students realized by their implementation. So even if it is a very simple algorithm, it works. This is the C language specification of the algorithm. I will not go through because we don't have the time here, but I invite those who are interested in this to look at. And you can try 3 different techniques. One is you simply have a RISC-V microprocessor, okay? That is this, with the data memory and the program memory, and you solve the problem by purely software RISC-V assembly problem, okay? It is possible to do that. By the way, if you will look at this in detail to this code, you will see that it is absolutely not the best one. It is simply just one solution that works. Second architecture, you can use a vector coprocessor similar to the Clasidra T1, so that you can use the vector intrinsic functions that we sketched in the previous slides. So this one is the solution. I think that in the slides that you have received, you have the full solution. So you can check if it is working. And sorry, for those of you who are very interested in hardware, you may design by means of System Verilog or VHDL, you may design a totally hardware accelerator that is memory mapped. And so, sorry, there is a, yes, this one is in the wrong order. Anyway, how do you do that? By means of a state diagram, you get to something like that. You can try to implement this. It is a state machine that is solving the problem, meaning that it is simply implemented the algorithm that was written in C. And finally, you get some results here. Simply to say that it is not always the case. If you are not very smart in designing your hardware accelerator, you see that, for example, the total energy or the cycle count of the total hardware implementation is not the best one, simply because you may not be very smart in designing the RTL accelerator. So don't be, let's say, don't be too much confident on the fact that if you do something in hardware, it will be faster. It is faster if you know how to design it. So if you design some more optimized versions, you can probably find out the way. You will find extremely good results, extremely big improvement in total execution time with respect to the initial data that is referring to the software sequential RISC-V solution. Okay, I will stop here. I am glad to answer any question related to the all the things that we have discussed this morning. Yes, I see there is something in the chat. What is the main difference between simultaneous multi? Okay. I will try to show you. I'm stopping sharing this very quickly. I can show you with a whiteboard. Okay, suppose that you have, these are the stages of pipelines in your microprocessor. Okay, so for example, this is the fetch stage, the code stage, and so on. In simultaneous multi-threading, you fetch multiple instructions here, and they may belong to different threads. So for example, you may have a red instructions here, but also a green instructions, and they are propagated in parallel through the microarchitecture, and then the dynamic scheduling hardware takes care of how to execute them so that there is no conflict, no dependency. This is something that Uri Weiser presented very clearly in his presentation. In the interleaved multi-threading, you have a single issue execution. So you fetch one instruction that is from the red thread, for example. At the same time, you are decoding one from the blue thread, and you are executing one from the green thread. But it is only one instruction executed per cycle. So the gain that you have here is that you don't have dependencies among the stages of the pipeline. The gain that you have here is more general, that you may have instructions from multiple threads. For example, here, you may be executing a red one, but also a blue one in parallel. This you cannot do with the simultaneous multi-threading. Sorry, with the interleaved multi-threading. This is simultaneous multi-threading. This is interleaved multi-threading. Okay, so why don't you do simultaneous? Because it is much more complex, extremely more complex. And the philosophy of interleaved multi-threading is to take advantage of having multiple threads, but having the simplest possible microarchitecture, because you don't have any control hardware to manage the dependencies between the instructions. Any other questions? You can also talk if you want. By the way, good reference explaining the microarchitecture. It is a bit of simultaneous multi-threading that is called hyper-threading in Intel microprocessors is a bit complex topic that I'm not sure is described in classic textbooks. So I suggest to go to just to the internet and Google hyper-threading or simultaneous multi-threading. It is strictly related to superscalar dynamic scheduling. So it is complex. The classic Hennessy-Patterson quantitative approach book is a good one for looking at the microarchitecture of superscalar microprocessors. Also, the microarchitecture of superscalar microprocessor is very well described in some articles by, if I remember well, by Gurisoy in some ISCA publications. Regarding interleaved multi-threading, it is much simpler. If you if even one of the article of my group can probably be sufficient for understanding how to implement it. Other curiosity, other comments? Okay, so it doesn't seem to be the case. Since we have finished our lecture, so it was a pleasure. Thank you very much, and best wishes for your career. Thank you. Bye.
Thank you very much, Mauro. Thank you everyone for all your questions and for participating in this lecture so actively. So we'll go to our lunch break now. You have 55 minutes, and at 2 p.m. we will see each other again here for a talk by Fabio Previtali from Almaviva. Thank you very much, everyone. Thank you again, Mauro. Thank you, Marcello, for your support as well.
Thank you.
See you.